Thank you. Good afternoon, ladies and gentlemen, and thank you for having the opportunity to come down from the high north to speak to this high-level forum. Actually, my country, Finland, is by definition a third of it part of the Arctic region, even if we don't have any coast to the Arctic Ocean. Alas, this is not about the Arctic, this is about the process relating to retrofitting environmental technology, in this respect ballast water treatment technology, on existing ships. The previous speakers have already, to a great extent, dealt with this issue. I hope to tackle it slightly from a different angle and by that way shed more light on the situation. But before doing that, and in order to put my presentation in the right context, please allow me just two brief slides about our company, ELOMATIC. We are a privately owned multidisciplinary consultancy and engineering company with headquarters in Finland and with 12 offices in 6 countries around the world, all in all, so employing about 700 consultants and engineers. We're not just into the maritime business, we're also into the shore-based mechanical design and process industry, like the chemical industry, and also into 3D software as a fourth leg. But to focus on the maritime side, what do? We do everything from conceptual design and development to detailed design of all the disciplines that involves ship design. We work with all types of ships, from big cruise vessels to small working crafts. We work with new buildings just as well as with conversions. And lately on the agenda have been the environmental retrofits. We're speaking about scrubber retrofits. There's a clear activity on that side now, and we are involved in a number of projects. Also converting heavy fuel-driven vessels to LNG. We have been involved in one such project, and actually the threshold for those have been lowered, so there are more projects coming up. And also on the ballast water management side, there is some activity relating to retrofits. One thing is common for all this environmental technology, and actually the process, regardless of which technology we are talking about. There's a clear, let's say, systematic way in how to deal with all this technology and retrofitting of it. So let's look at this process, which we actually have defined into 4 various phases. It just so happens that the phases happens to be exactly the same as Mr. Kokarakis presented here in his presentation. We have not discussed with BV, so this just proves that this is the way it should be made. The first phase here is actually choosing the right solution. It includes a lot of activities. I'll shortly come back to those. The second phase, it's actually the custom-made integration design, also in shipbuilding terms called the basic design. Moving on to phase 3, which is then the detailed design and the planning of the actual execution. And the final phase is, of course, the installation, which aims at minimizing the off-hire here. The process is systematic. There's a clear input and a clear output between each phase here, starting with the question mark, what to do at all, and ending with the let's say, the commissioned plant. And there's a number of considerations which have to be taken into account. But let's walk through these various phases one by one, starting with choosing the right solution here. This is going to be rather short because of, and simplified because of the time constraint here. The ideal objective in this phase is, of course, to find a reliable solution to the lowest total cost of ownership over the ship's life cycle. And here again, there exists no standard solution. Each ship should be dealt with individually. Even sister ships should be considered individual. This phase forms actually an extended feasibility study and includes a lot of evaluations, starting from technology and solution consequence evaluations, cost calculations, and actually in the final end, so you end up with a short list of feasible solutions, and then you can enter into a let's say, more commercial, technical, final negotiation. But as I said, there are a number of considerations to be taken into account. The previous speakers have already dealt with these. I'm not going into them in detail. However, we are talking about, first of all, the ship type and size, the trading pattern and routes, which kind of waters the ship is navigating in, the ballasting profile, the performance needs, how frequently is the ballasting, what are the flow rates required, etc. There's a number of technical aspects which will have to be taken into account. I will slightly revert to the physical dimensions here because that's one of the most important ones. Also, the operational aspects, ranging everything from reliability, accessibility, crew training, etc., so are important. But finally, what usually always counts are the economical aspects. What are the capital expenditures and what are the operational costs over the ship's life cycle? And this is just one example where we have compared 12 various solutions here, where the year 0 represents the initial investment costs and then added with the operational costs over the year. And here you can clearly see that the one which is, let's say, has the cheapest investment, or is the cheapest investments already after a couple of years, it's definitely starts to be more costly, whether some of the other solutions act in another manner here. So also the remaining lifespan of the vessel has an important impact of the choice of solution here. This example was for 100,000 ton combined crude oil product carrier with 5,500 let's say cubic meter per hour capacity. Moving on to the space challenge, which was already also addressed by the previous speakers here. This might prove one of the biggest challenges on existing vessels. And it's also to evaluate the space and the consequences of the installation is an important support for the decision making here. So if you have a number of shortlisted solutions which otherwise technically and economically seem the right ones for you, you should still at an early stage make this space evaluation. And in this respect, so the state-of-the-art design tools can be utilized in order to achieve high accuracy. And one way to achieve this is the laser scanning, which also was presented here in the previous presentation. What this is, I'm not going into that in detail. That was already mentioned here, but there are clear advantages why to use this. This is evidently needed when there's poor documentation of an existing ship, or when old system and not perhaps updated drawings are available, especially when the space is crowded. And thus it will ensure a high accuracy as built status. It will reduce the needs for ship visits, and you can reduce the number of design errors. I'm not saying eliminating, but I'm saying reduce. Of course, that has an impact. And finally, there's definitely potential to reduce the total cost in this respect. Mr. Kokorakis had a very nice video showing the point cloud here, which was turning there. I'm more modest and I'm using this still image here. And the gray areas you can see are the point cloud there, whereas the colored areas are and elements are the new equipment which is fitted in. This is just one example. This is another example. Again, the gray areas represent the point cloud, and the colored areas the equipment to be installed. This is a much smaller vessel here where we try to utilize existing space as far as possible. This is actually the same in a more nicely visualized way, and the objective here was not to have any structural modifications to the ship at all. However, as it turned out, so technically this vertical solution utilizing pump room and the stairwell would not be able, so we had to modify the solution and make, let's say, modifications to a tank here. That's the blue area shown here. Again, that of course added to the total cost and to the decision of the owner in this respect. Anyway, having gone through this process, so you end up with the short list and in the final end with your decision with whom to go with. And after that, so the process becomes much more streamlined and I'm not saying simpler, but more streamlined. We come into the second phase here, the integration design, or as I said, the basic design here. So that includes a number of drawings, and it actually, I'm not going to go through those either here. All of them can be read from the slide, but this finally, so it ends with the classification approval and authority approval of the documentation here. I would just like to add here that it could be also beneficial to use so-called CFD analysis, computational fluid dynamic analysis, in order to verify the capacity and the functionality of the flow here. So let's move forward to the third phase, the detail design and planning. Again, that can start once all the approvals are in place. Of course, you can start earlier with that if there's a rush, but again, then you may, let's say, do that on a risk. And this includes all the working drawings, prefabrication drawings. That can be an advantage if you want to shorten the downtime. Material definitions and part lists and specifications. Then part of that process is also the component and material procurement, contracts either with yards or contractors, and also taking into account the installation accesses and routes. And the factory acceptance tests can be seen as part of this phase here. So let's move over to the fourth phase here, the final one, and with the objective to minimize the off-hire. Before doing that, so there are, a retrofit can be actually, you can contract that in several various ways. You can do it in a traditional way, in the in-house managed, which is in-house managed. Then you, let's say, order equipment, material, engineering, and the installations one by one, separately, cherry picking, and in that way try to, let's say, minimize the overall cost if you have the capacity to manage such a project. Then the total opposite is, of course, a turnkey contract with the equipment supplier, provided he has this capacity, and in that case, the phase one will become emphasized in the selection of the supplier also. You can utilize the traditional solution where you make a contract with the shipyard or repair yard, and you deliver the equipment as owner's supply, and then the yard will do the installation, perhaps provide the engineering, or that can come as owner's supply just as well. Or you can use something which is used quite frequently in land-based installations, which is called EPCM solution. Then let's say you outsource the engineering, the procurement, and the construction management, in which cases the phases 2 to 4 are emphasized. Then to do it at the shipyard, or as we earlier heard here, also can done while the ship is in traffic. That's of course one thing to consider here. In generally, so the shipyard installation is of course a very safe one, and is definitely justified if you can combine it with the scheduled docking. It's worthwhile to do preparatory work so you can minimize the downtime at the yard, but to finalize it at the shipyard it's also preferable. And the definitive advantage in this case is that you will have the logistics, the labor, and all the material there in case you would run into surprises. Okay, the disadvantage may be if the installation time is long, that you let's say would be at the yard longer than a normal streamlined scheduled docking, and that will be more off-hire costs, of course. But there are examples that installations can be done while the ship is in service. It's definitely a technology dependent. It doesn't apply to all technologies. The design is in a key position, and it requires extensive planning and also a high degree of prefabrication. You should use solutions which can be done in order to minimize the hot work, like pipe couplings, etc. But the logistics may turn out a challenge here. I mean, if you run out of some materials, labors, etc., depending on your trading route, you might be in big trouble, and this may last a long time. There are examples of this also from the real situation. So, the time frame, definitely an important issue to consider here. Let's look on the various phases and the duration of those. For the first phase, you should definitely allow 3 to 4 months to have at least a good grip of what you are looking at. Then phase 2, the integration design and the approvals allow at least 2 to 3 months for that. The same applies for the workshop drawings and possible prefabrication here. And then for the final phase, for the installation, so depending on solutions, to 2 to 4 weeks. All in all, this will turn up to about close to 1 year. I think Mr. Kokarakis had 9 months to 18 months, but this is somewhere in between. Yes, I'm stopping right now. One more slide. Yeah. And don't forget, let's say, the delivery time of the equipment itself, and of course the due date being as according to the new revised implementation, according to IMO or US Coast Guard if you are sailing on those waters. Then finally, some recommended actions here. Start with the phase now in order to find the most suitable solution with the knowledge of today. But you don't have to push the procurement button, but you should know where you stand at least. Then it makes it much more easy once this enters into force. Carry out the laser scanning already now, and especially at the next dry docking, to verify the starting point. Especially in tankers and with ships with EX classified areas, to do EX scanning while the ship is at sea is very expensive, but to do it at the shipyard, it's definitely not expensive. It's just a one-day work for two guys. And also tackle the space challenge by carrying out this pre-integration design and the space evaluation. Establish suitable partnerships already today to be prepared for the coming. And finally, if you put sufficient of efforts in the beginning of the process, that means investing small, you will save big in the end. Thank you very much for your attention.